Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this specific discussion, we're going to look at specific forms of equilibrium constant, and we're going to consider gaseous states of this particular, of course, equilibrium constant in this specific discussion. Now, in our last discussion, we had said that we can be able to derive the thermodynamic equilibrium constant using a general reaction, and I'd given a general reaction for the reactions of A, B, and of course giving the product of a C, a D in that specific case, and we're given a general case for this particular case for R, L plus M given as such. And of course, this, as we said, represented the general case of a reaction which is consisting of this species of reactants and the products given as such. And we'll say that we can be able to find the Gibbs free energy of this specific reaction, general reaction, by finding the difference between the values of the energy for the product minus the reactant given as such. And we would say that this one can be achieved from the general, of course, equation of Gibbs free energy over each of the species for the free energy, which is going to be expressed in terms of G standard, and then RT, the natural log over A, whereby we said that at equilibrium, this specific value for delta G is going to be given as a 0. And of course, considering this specific species, from the general equation, we see that these molar coefficients are going to represent the various volumes of this particular species. And of course, from the ideal gas equation, we're going to see that this particular species, or the coefficients, are going to represent the various concentration of the molar concentrations, as I've said. And later on, we're going to see that there's a relationship between these specific concentrations and the activity of the various substances for the species and the products insofar as their partial pressure is concerned. Therefore, in this particular discussion for today, we're going to find a form of equilibrium constant that we can be able to describe in terms of a partial pressure and the concentration. So therefore, we had generally said that this aspect of equilibrium constant can be given in the form of an equation, whereby we said that this delta T naught is equivalent to negative RT, the natural log of this specific coefficients we had given for A, L, A, M, and then all over A plus A, B given as such. And we see these coefficients can go on in that specific order together for another particular coefficients which may be present in this particular case. And we said that at constant temperature, then therefore these two aspects are going to be constant. And then, as we said, in fixing two particular variables, and therefore we're going to have the third variable automatically fixed. And therefore that one led us to a conclusion about this specific aspect of the equation giving us the thermodynamic equilibrium constant of a specific reaction. So generally, I'm going to consider the case, of course, of a general reaction of species A and B, and we had said that this is going to give us the product of L and M from this particular illustration that I've given. So this is going to give us make work easier for us. So if I say that A and B are reacting, therefore from the demonstration that I've given, it's going to give us an easy way of perceiving this specific concepts. So this is going to lead to the product of L and M as I've illustrated. And if we consider the case of an ideal gas, then therefore we're going to see that, as I've mentioned, the behavior of each of these particular substances is going to be proportional to their partial pressure and their molar concentration. Therefore, we can be able to give the equilibrium constant of this specific reaction by considering their partial pressure P, of course, which is going to be given in terms of P. So this partial pressure is basically given as this particular form, but for the case of regularity, I'm just going to give it in that specific implication. So we're going to have Pm given as such, and then it is going to be over A, and then B given as such, and these are going to go on and cater for another variable which may be contained in that specific case. So this is going to be the general implication of a partial pressure insofar as equilibrium constant is concerned. And this is the first form of equilibrium constant that we have given in terms of a partial pressure. Now, if we consider the molar concentration, of course, of these various coefficients that I've given. We can have a second version of this thermodynamic equilibrium given in terms of this molar concentration, and that is going to be given as K subscript C given as such, and therefore this is going to be given as C L and then superscript L, and this is going to be also C A C B given as such. So as we are going to note as we go by, this specific enumerator is going to cater for the, of course, the products, and the denominator is going to cater for the reactants coefficients in that specific case. So having talked about that, we can be able, or we can consider the case of an ideal gas, as we said. As we said, these particular forms of equilibrium constant are going to be represented using the molar or the ideal gas equation. So I'm going to do away with this, and I hope we will be able to remember this particular aspect of Kp and Kc for the molar coefficients, of course, and the partial pressures of those specific reacting species and the product respectively. So from the ideal gas equation, PV is given as nRT, and of course in this particular scenario I'm going to consider the case of PL, which is going to represent the relationship between this one, and this is going to be given in terms of NL RT given as such. So we can be able to consider this particular pressure or the partial pressure in terms of P given as NL over V RT. And as we said from the concept of the molar concept, we can be able to see the ratio between the number of moles and the total volume as concentration. So this basically first part of the equation is going to describe the aspect of concentration. And from the equation that we have given for the equilibrium constant, the thermodynamic equilibrium constant for the that specific concept of molar concentration, therefore we can be able to derive an equation from this representation of pressure, having it as C, of course, LRT given as such. So from the ideal gas equation, this particular fashion is going to give us the aspect of pressure. And therefore, we can be able to do a derivation of this particular value for Kp, giving it as Kp. And we're going to do a substitution for, of course, the aspect of pressure, which is the partial pressure given, using this specific right side of the equation that I've given for concentration. So therefore, we're going to have this one represented in terms of C, of course, LL, and CM, capital M given as such, and this is going to be CAAC BB, and this specific equation is going to, the ratios are going to imply, of course, using this specific aspect for concentration, and these are going to imply, of course, RT, which is going to be given in terms of RT, and then so if this one is going to be the coefficient from logarithms, we can be able to give this particular form of a coefficient in terms of power or an exponential. Therefore, this is going to be consisting of the range of coefficients which are going to be displayed for this particular case for LM for the, of course, the products, and the AB for the reactants. So therefore, for the numerator, we are going to have this one RT given in another fashion of an exponential, whereby we are going to have these specific powers given as L, M, plus, and then all over the denominator is going to be given in terms of RT, and then we're going to look at these specific coefficients being given in terms of AB, and then plus other coefficients which might be given in that particular case. So therefore, we can be able to express Kp in terms of Kc, which is going to be given in a form of course, Kp is equivalent to Kc, having taken note of this specific transition, and then we're going to have it given as RT, and the exponential can be summarily given in terms of delta n given as such. So therefore, therefore, we're going to have a general representation of this specific form of equilibrium constant given in terms of Kc, where this is concentration, of course, and this one I'm going to gather for these specific ratios that we had given from the molar gas or the ideal gas equation. So the concept of a delta n, as I've said, which is going to constitute these specific elements of the exponents, are going to be given in terms of L plus M, and then this one minus A plus B, and then there's a continuation of those, which are basically the difference between the exponents for the numerator and the denominator are given as such. And of course, this is going to be depicting an increase in the number of molecules in a chemical reaction, which can be written in that specific form. So in summary form, I've said that we can be able to give various forms of equilibrium constant, and we consider the case of an ideal gas equation, which is going to give us a different version of the relationship between this and this particular molar coefficients I've given as such, and that is going to reduce into a form of an equation which can be given as such, giving the relationship between the equilibrium constant at partial pressure and concentration using that the general representation. Now, I hope that we have understood how we can be able to represent various forms of equilibrium constant, especially considering the case of an ideal gas using those specific symbols I've given and the elaboration on the concentration and molar coefficients, which I've already mentioned in this specific discussion. So kindly check our description boxes for various links of other videos, which are going to be assisting us, of course, have various interpretations of this concept of course, equations of equilibrium constant, and of course, other related topics. So that is it for now, guys. Bye, God bless.